upgrade my Maple, so I uninstalled the old version and tried to install the new one, but I got an error which my computer doesn't have enough space. So I have to go to IT to fix it. So I promise to do it as soon as my Maple problem is solved. But for those of you who are interested to look at it as soon as possible, you can find this Maple file. Where is here. In this Maple file, you can go to the device section and look at the examples which are there. But as I said earlier, if I can fix my Maple problem, maybe today, later, or next week, I will show you as well. But you can also use this file. Okay. Today is again the continuation of LaPlace, and we will cover or talk about the new signal, which we'll call it the unit impulse signal or function. We will talk about how we can find the Laplace of such a function, and then we talk about the linear time invariant system transfer function and poles and zeros of LTI system. And again, as usual, if you find some blank page in the slides, this is for your own use. So first, what is this unit impulse function? Or another name for it is direct delta function. If you remember, in table 7.2, we have this rule for t to the power of n times u of t. And if we take the Laplace of it, this would be the general formula for it. As you know, Laplace has a linearity properties. And this n, yes, thank you. This is a number. So depending on what is n, it can be 2, 6, or some other numbers. So because of linearity property, what I can do here, I can multiply both sides of this by 1 over this. So if I do that, it will become t to the power of n times u of t. Again, the Laplace, it will become 1 over s to the power of n plus 1. And this is valid always. And if you, I don't know if you remember it or not, if you have a two-sided arrow, it means that we can go either this way, which is Laplace, or back another way, which is inverse Laplace. So down here we have inverse Laplace from this side. So another rule which you became familiar with it was the Laplace of the first order derivative. It is also in table, I think 7.3, that for a function f with the Laplace of capital F, the first derivative Laplace would be s times f of s minus f of 0, which is the initial value. And if this is the initial value, and if it's 0, this is the rule for first order derivative. What I will do now, I will use this side for now, and I try to compute what would be this term for different values of n from 0 to infinity. If I do that, then you have the first, the second line in this slide. So, for different value of n, if n is 0, this will become 1 times u of t. If n is 1, you have t to the power of 1 times u of t. For for n equals to 2, we have different term till n. Of course, I can use this side and obtain the Laplace for each of these terms as well. So these green arrows are for Laplace, showing we move to the Laplace or estimate, and this would be the form formula for each individual term. Now a question which I have. Let's look at the term we have for n equals to 1 and n equals to 0, which is t times u of t, and then we have the other one, which is 1 times u of t. How can I reach this one from the first, the one I have in the left? Any idea? Yes?
Times 1 over t.
Yeah, this is 1. So I write it here. Now, if I go for another one, which is n equals to 2, I have t2 times 2 factorial times u of t. Now, if I want to go from this one to the middle one, so I write this one for here for now. Is it still times 1 over t? Yes?
So now it's 2 faculty over t.
What? Can you repeat it?
2 faculty over t.
Over t. Yes, this is also still correct, but the relation you have here is not the same as what you have here. Now I'm looking for something which is valid for all the arrows you can see. There is no arrow here, but if you put an arrow there, I don't know where is the pointer here, but I'm looking for something very, very general, which for all the second line here, for instance, for n equals to 4, I can use it to go to n equals to 3. Again, I use the same approach for n equals to 3 to 2 and so on. So these are not wrong, but I want to find something much more general. Something which is valid in all of them.
Can you differentiate it?
Exactly, differentiation. Why? Because if you make a derivative of this one with respect to t, you get this one. If you make the derivative of this one with respect to t, you get the other one. And this is correct for all of them. So if you start at n and make a derivative with respect to t, you get the exact term for n minus 1. And so on and so on. So for the first line, we can say that if you take the derivative, we get to the other one. Now let's look at what we have down here. So can we find something general? I mean something which is valid in all of them again, such that I can use to move from here to there, and from here to here, and from here to here? So, for instance, I want to go from 1 over S2 to S, to 1 over S, and also from, what's the other side as well? Yes, please. Yes, exactly. So if you multiply by S, and also it's correct for the other ones. So I just wrote all of them here. So here, if you multiply all by S, this is the multiplication by S, then you go from this to here, from here to here, and so on. And at the top, for derivative, I use the D parenthesis notation. So this D, which you can see at the top of arrow, are derivative. So now I will follow the same rules one more time for each of these. So for 1 over S, if I multiply it again by S, I get 1. And for the top one, if I take the derivative of u of t, so the derivative of unit step function, what we get, this is a question mark. This is something which I will explain or show you today. But this question mark is something that for sure the Laplace of it should be always and always equals to 1. Because again, the bottom ones are the Laplace of top ones. Now let's see what is this red question mark. For now, I will define this direct delta epsilon of t as u of t minus u of t minus epsilon divided by epsilon. And epsilon is some small number. So what I do now, the direct delta of epsilon of t is u of t minus divided by epsilon. Now I want to plot only the numerator, only the top part. If I do the plot, of course this is t. U of t, we know that it's unit step, so it is this one. So the white one is u of t. Then we have u of t minus epsilon. And again, if you remember from last week, it means that we have this unit steps with epsilon unit shifting to the right. Am I right? We did the plot of it with different values last time. So if I assume epsilon is here, this is just as an example, then the blue one here is u of t minus epsilon. Now I want to do the subtraction of these. So for the range of, I use another color. For the range of minus infinity to 0, so we are here. So everything is 0. So still the plot is 0. For between 0 and epsilon, we have white one here only, and still the blue one is 0. So if I want to do the complete blue should be here as well. So 1 minus 0, we have 1. And then here is 1 minus 1, which is 0. So now we have this region. And this is the plot only for the numerator, for the top term. But I have to multiply this by 1 over epsilon as well. And epsilon is very, very small number. So if I multiply this by 1 over epsilon, so it's not the unit, it's not the height of 1. The height will be changed to 1 over epsilon. Because you multiplied your plot with some 1 over small number. And this is what you can see also here. As I said, this epsilon is small value. So what I do now, I take the limit of this as epsilon goes to 0. So what does it mean? Actually, it is in the first line. We take the limit of this direct delta epsilon in a way that epsilon goes to 0. So this epsilon now moves from here to this side. So it will become smaller and smaller and smaller each time. As the epsilon becomes smaller and smaller, what will happen to 1 over epsilon? Yes?
It will go towards infinity.
Exactly. It will become bigger and bigger and it goes to infinity. So now, I use the orange color. So it goes to, this epsilon goes to infinity. So this one, of course, epsilon is not here anymore. For instance, maybe it's here. So it goes maybe here, and this is 1 over epsilon. So this is what I have in the right side of the plot here as well. So as we can see, this limit, we can say that at the number goes to 0, almost we can say at 0, it has the value of infinity and 0 elsewhere. Actually, this is the definition of this direct delta or impulse function. The notation we use for it is always this delta t, and if we back to this, which we had it before, the question mark, which is the derivative of u of t, is the direct delta. Why? Because the one which I wrote here, this direct epsilon of t, this is the definition of derivative of a function. I'm sure you have seen it in other math courses. So when you want to take the first derivative of any function, this is how you should do that. So the derivative of unit function is always direct delta function, delta t. So the question mark is this box with the Laplace of 1. And you have seen also in the tables that the Laplace of direct delta is always 1. So all match together. Any question regarding direct delta? So it is an impulse or a very big push which you put to the system.
I have
Okay.
a question.
Yes?
What the orange function there? Why does it go like up there?
Okay, you know, this epsilon every time is very small and small and small. So for instance, I just give you an example. Epsilon is 0.00001. And now the height is always 1 over epsilon. So 1 over 1, 2, 3, 4, 5. So it will become, if you do the math, it will become, I think, 10,000, if I'm not wrong. So you can see it is very big compared to epsilon. That's why it goes toward infinity.
Okay, but is it still defined like in the bottom, or shouldn't it just be defined at 10,000?
No, actually it starts from, of course, here and goes to infinity.
Okay.
Yeah. So in a y-axis, you can say it's almost here. Oh, sorry. But yeah. Okay. Any other question? Now let's look at here. Now let's consider a function f of t, which is a continuous function at t equals to 0. So at origin, it is a continuous function. What does it mean when we say a function is continuous at some specific point, like origin? It means that the limit of the function at t goes to 0 is equal to f of 0. For instance, one example for continuous function can be this one, which at t equals to 0, we have, of course, f of 0. Now, let's multiply this with the direct delta function. So, the direct delta function, based on the definition we have, it has the value of infinity at the origin and 0 elsewhere. So, whatever function you have, because of the multiplication, all this region becomes 0 now, times direct delta of t. So here it would be 0, here it would be 0, and only at the origin it is the multiplication with the direct delta. Actually, this direct delta is very powerful, and again we have a good tables which you will use them in the signal behandling course as well. So if you go in an extra folder of your Learn, you can find the table there as well. In the table, this is impulse. Here, table 2.3. I should maybe make it bigger a little bit. These are some properties of the direct delta function which we will use them in this course and also some other course. The ones which we will use it because save it on your laptop, you will use them a lot. And you will use this property, as I said, in the signal handling course as well, in a fall. Okay. Now let's see what is the integration of this direct delta function. So now we want to take the integration of minus infinity to infinity of direct delta of t dt. Based on the definition of direct delta, we know that direct delta is this limit of direct delta epsilon of t, and as the epsilon goes to 0. And then of course we have dt. What I do, I will take the limit out and do the integration first. So what I write is the limit of epsilon goes to 0 of what is this integration result? So integration of minus infinity to infinity of direct delta of t dt. So what is I have it. No, so if I change this to 1 over epsilon, then I have this graph. Because now I want the result of minus infinity to infinity of the this direct delta of epsilon, and as we know, integration means the area under the graph. So what is the area under the graph for this? We have this one only, the middle part. So I want to find this area.
1.
Exactly. Why? Because it is a rectangle shape of 1 epsilon multiplied by epsilon. So the result of this integration would be always 1. And the limit of 1, I see it is 1. We can also obtain the integration when you multiply it by a function. So this is board number 2. So now we want to find the integration of minus infinity to infinity of multiplication of function f of t with direct delta of t dt. Again, few slides before, I told you, or I showed you, when you multiply a function with direct delta, the only term or the only valid point you have is when t is equals to 0, and the rest are 0. So I can replace this with f of 0 now. And it means this is f at t equals to 0, okay? So you have some specific value for it. It has some number. So this can come out of integration because it's some specific value. And this is what I just showed you here, which this would be always and always 1. So it will become f of 0. I think this is the proof of one of the lines in the table 2.3. So that's why that the integration becomes equals to f of 0.
Can you just, at the board,
Yeah?
this side of the room can't see the...
Oh, maybe from here.
Yeah.
Can you see it up here?
Yeah.
So this is equals to f of 0. Okay.
value of the, that was it called, direct
Direct
delta?
delta or impulse.
Yeah.
No.
But is the value 1?
No, actually it is infinity, but
Yeah.
in your book, the author, I don't know why, but I can see that they consider it as a 1, but in reality it's not 1. It is a very, very big impulse or force you implement.
But if you multiply anything by infinity, it will become infinity, right?
Yeah.
So it's, yeah.
That's why it's called impulse, because you implement for instance, if you implement it to the, for instance, you have a baby on a swing, and if you suddenly, because of some reason, you do the push force or impulse it, of course it will become very crazy and big, and hopefully the baby is safe. Then, in reality, it is something big. But I also don't understand why in your book it showed it with 1 as well.
But I'm just saying because the result here becomes f of 0.
Yes.
So it becomes the original value.
At
of the
point
function.
0
Yeah,
only.
at point 0, yes.
Yeah.
But then it's only then the value of f at point 0 has been multiplied by 1 and not by infinity, right?
Yeah, because you multiply it by this integration and not by direct delta
Alright.
only.
Yes, alright. Yeah.
This is the difference.
Yeah.
If you multiply it by only direct delta, yes, it's something big, infinity. But here you multiply it by integration, which
Yes,
is 1.
Alright.
Okay. Like unit impulse, which we can implement it to the system or have it with the delay, you can have the direct delta with the delay as well. So, for instance, here you can see the direct delta with t0 unit delay or shift to the right. But the property of it is very similar to direct delta itself. So again, we can prove that the integration of direct delta with the delay is also equals to 1. Like the proof I did here, you can do the same for this one and prove it. And here you can see I also put it 1 because in the book it was 1 as well. So direct delta itself has a Laplace of 1. This is something we saw it earlier. But if you want to make it as a very general formula, because we can have direct delta with the shifting, the Laplace of it is the one you can see in the second line in the right. So it is the multiplication of e to the power of minus t0s. I think you can find it in the tables as well, if I'm not wrong, but you have it also here. Now let's look at an example. I want to give you 5 to 7 minutes time such that you try it yourself first and then we solve it here together. But let's look at it. We have this differential equation which is given to us, and it says with the zero initial condition, the only thing which you should pay attention is this one, which x of t you have in your differential equation is equals to unit step function. So now you have 5 to 7 minutes time. So yes, and then as I said, we solve it here together. We talked about it in the class. What is the differentiation of u of t? It is in the slides, so if you go slides back, maybe you find it there.
Yeah.
jeg tænker, densitet må være hypertekst. Det er en over et. Det er jo totalt. Ja, det står her. Ja, en over et. Og så er der det der x der, det må du tænke det som om, det er jo så udmærke af ting.
Ja, det giver lidt oplevelse.
Så får du den her, ikke? Så fordi at mærke af ting, det giver s gange over f til minus 100. Så du får bare et mærke af ting til plads.
Lagt tabellen sammen, eller hvad?
Nej, det er faktisk og den der 0, den der 0 til det.
Der er ret mange.
Ja.
Det er sgu meget fedt. Også fedt at have en partner med til at lære det. Det er sgu meget godt, men altså, jeg er ikke sådan super stærk lige på det her. Det er også. Det er jo også sindssygt. Jeg kan se, at vi skal løse det.
Det er vildt nok, du kan løse det.
Det er imponerende. Det har jeg faktisk ikke. Det vidste jeg ikke. Så har jeg gjort det med velkommen i klubben.
Ja. Og så må det jo så give noget gange op. Ja, det vil gange 1.
Nu er vi skal. Jeg har sgu da løst den herovre.
Det er til en uretid, så må
Der er masser af
det
der
mærke
løst.
til, hvad en udmærker ting, ikke?
Frederik har bare gjort det.
Frederik har løst. Lige så lige snakke om det.
Og så de her, de er jo så til funktion.
Så den er lige 0 at tage. Jamen, så man kan få 2 gange 0 her. Nå. Det er bare store y. Eller AS.
Ja, den der. Ja. Hey. Det er det, ikke? Ja, det var den der. Ja, det der dobbeltmærke, så du bliver en mærke.
Den der dobbeltmærke.
Ja, den bliver til S i anden. Ja. Ja. Og så bliver det så. Ja, og så efter 0. Men det er jo så bare 0. Ja, det er hele første dimension, du kun lige første. Så det er den der, ikke? Jo. Og det er S i anden gange F af S. Det er den der. Det er 0, så kommer det til at stå 3 gange, så må det være F af det samme. Ja. Bare hvor det er første. Så det der bliver 0. Så kommer 3 gange den der, og så den der. Den er også 0. Nej, det ved jeg ikke. Jo. Y af den der, det må bare være almindelig, ikke? Så det bliver F af S 2 gange S. Ja.
Ja, så det er kun lige for at det om det skal mærke til, om det er til løgnet.
Ja, ja.
Der står der stop. Det er små ord her. Det står.
Så må der også
Den der også.
så må det mærke til jo også være
Det er sådan lidt mere overskueligt på de der øje. Det der er også lidt. Ja. Men du skal lige ind og... Ja, der er nogle af dem, jeg kan lige sende til dig gennemsnit. Der er nogle af dem, der vil forkert. Det er så bare lige den her oplæg. Præcis, det er bare den her.
Ja. Jeg må udgøre det.
Men ja, LaPlace. Det er jo UT LaPlace. Det er gode idéer, tror jeg. Det var vel den her. Er vi ikke enige om det?
Jo, så er der nogle nuancer. Ja, så er det den der i.
Det er vel den.
Men så også nej, jeg har sagt
Okay, can we look at it together or you want a few more minutes?
Let's just look at.
Okay. So, yes?
No,
Okay. But you have seen solving initial value problem before. So solving this problem is not something new. The tricky part is here. Why it's tricky? Because sometimes students read the question and say, okay, x of t is u of t, and they will replace this by u of t. But they forget to pay attention to other terms. Here it says the first derivative of x. And some of the students will use the tables rules and do the Laplace here. But before that, this is the first derivative of x. And your x is u of t. So it means you need to replace this with the derivative of u of t as well. But what is the derivative of u of t? Yes?
1.
No? No? It's direct delta. Thank you.
But
So-
okay, I need to ask about direct delta because it's not a triangle when you say.
No, it's we can say it's infinity at t equals to 0.
Yeah, but
Så laver du plads på den. Selv jo 1.
the symbol is delta. It's
What do you call
Men det er
it?
jo først, da du
is that
Det er
I
bare
think in
forhold.
Greek they call it
Det er jo ikke
delta.
det spørgsmål, også.
Det er lille delta. Ja, okay.
I think it's in the Greek language.
Ja.
They
because
call it
delta
delta.
normally is a triangle.
This is the capital delta. The triangle is the capital letter, and this is the small letter for it. At least based on my knowledge, maybe I'm wrong. You can double check it. But as far as I know, this is the small delta, and in Greek, this is the capital delta.
So that's a small delta.
Yeah, and this is capital. Yeah, like English and Danish, which have lowercase and uppercase, so they have the same. So now, here, the derivative of this one, if you go a few slides back, it is here. You remember that I told you that in the second line, the general formula we can use is that we take the derivative of previous one and then we get the new one. So here is the derivative of u of t, and I showed you, and at least I think I showed you, that the question mark, which is the derivative of u of t, is a direct delta function, delta t. So I can replace this here now by direct delta t as well. And this is a part which the students make mistake. So always read the question carefully. Now, we want to do and solve this initial value problem. So as you remember, I told you last week that the first step is to take the Laplace from both sides of the equality. And we have 0 initial values, so all of the initial values are 0 here. So if you use tables, it will become S2 capital Y of S plus 3. If any term is not clear why I write this, just ask. Times Y of S plus 2 times Y of S equals to the Laplace of u of t. Again, look at the table. It is 1 over s. And the Laplace of direct delta is 1. Here, I can make the factorization of capital Y of s. And for the right side, yes please?
Can you briefly explain why did you remove the in the first part big Y of S but it's not like, is it because it's 0, you
Yeah.
remove the S after? No, it's called, minus S,
Power of.
power of minus 1 times F to 0.
Okay, I think I know what's the question. Just to make sure that I understood it correctly. So yeah. Let's talk about it. So in a table again. This is a spring problem. I think I should go over that. If I understand your question, you are asking why. Where is the first derivative? It's a bit off. Your question is, what happened to maybe here or here? Exactly.
Yes.
Okay. Again, last time I told you that we read this, we assume there is no minus or plus there. So it means f of 0. So f at t equals to 0. Or again here is f at t equals 0. So they are initial values. And in the problem we are solving, it's precisely mentioned that they are 0. So it's here. That y of 0 is 0 and y prime of 0 is 0. It's in the first line.
Okay, but
That's why they are 0, so I don't write them.
okay. Okay.
So if the values of initial values are 0, it means that they are 0. Nothing will happen with them, so we can just remove them and not writing them. Any other questions so far? Okay. So here I take the factorization. For the right side, what I do, I combine this as one rational function. So how I do, this has the denominator of s, so I will generate the denominator of s here as well. So what I do, I multiply it by s and divide it by s, so it can become as s 1 plus s. So I made it as a one rational equation only. What? No problem.
What magic did you just do?
I haven't done anything. Just, what is x over x?
1.
One, exactly. So here, I want to change it in a way that this, so are you agree that this is 1 over 1 as well?
Yeah.
So I want to change it in a way that the denominator here becomes the same as what I have here. So both become s. So I multiply it by s and divide it by s. So mathematically I multiply it by 1. So nothing again changed here. So now I can remove this. So it is s over s. The denominator in both are the same. So I can add them together. I did it. The denominator is the same. And the numerators will be summed up together. 1 plus s.
That's hard.
So, but I'm happy that you asked, because if you don't get it now, it will become much more confusing later. So just ask. Okay. Now, from here, I can obtain y of s, because I can use what is in the right side, which is 1 plus s over s, and divide it by coefficient of it. So it is s2 plus 3s plus 2. So now I have the y in frequency. But before going any further, first I try to simplify this function as much as I can. Again, I can write this as s2 plus 3s plus 2 divided by 1. So I multiplied those who are far from each other and write it here as a top. This is what we do in a math. And here, those who are close will multiply by each other and comes in a denominator. Of course, you can use Maple to do completely, but I don't have enough space for rewriting it. When you want to take a picture, come close and take the whole picture. Sorry. So, I have y of s now, which is 1 plus s over s times s2 plus 3s plus 2. This is what I have there. Now, when I want to solve this problem, at the end I'm interested to find y of t. This is the final answer I'm looking for. So if I take the inverse Laplace of it, then I have the answer.
Can I ask,
Sure?
why is it always we take the inverse Laplace?
Because when it solve a problem like this one, it means that find the output signal or y of t here in this specific case in time domain. So when we have it in frequency, in order to get it in time, so we should always use inverse Laplace, and that's why we do. Because we move from frequency to time by using inverse Laplace.
Okay, and so you're going from time to frequency.
And then frequency to time. Exactly. So we don't see this in table like as it is. So we need to do partial fraction expansion. Can anyone tell me which case of partial fraction expansion I have here? Yes, please.
Case 3.
It's
No.
not correct.
Not.
It's not case 2, so that's case 1.
Oh.
It's case 1, but let's see why. Let's see why. First of all, let's look at what we have in the denominator and find the roots. If we put it equals to 0, so I will put s2 plus 3s plus 2 equals to 0. I can write it as s times s plus 1 times s plus 2 also equals to 0. Again, you don't need to write it as it is, just use Maple to give the roots for you. But you have 3 roots. At 0, and minus 1, and minus 2. So I have 3 roots which are real and distinct. So it's case number 1. Also, another thing you can do, which will not have effect on the result on the conclusion of case, is that this one, as I said, can be written in this format. So if I do that, this will become s times s plus 1 times s plus 2. So this s plus 1 and s plus 1 cancel out each other. So your f will become a little bit simpler. Then it's easier to do partial fraction expansion as well. So it means this one goes out. And it's still, you have case number 1. So always and always, if you can do the cancellation, because it helps you to have a simpler partial fraction expansion later. So we have case number 1 of I can understand why you assumed it's case number 3, because maybe you looked at here and you said because it has very similar structure of the example we had before, so it should be case 3, but always use the roots. Then you are 100% sure about the results. So let's do the partial fraction expansion now together. So y of s is 1 over s times s plus 2. And because it's case number 1, I know that I can read it in this format. Again, if you don't know why, just let me know. I will repeat it again. We have 2 roots, so I can write it as a 2 summation. And each source of the roots come down here, and we have 2 unknowns. Now, because it's case number 1, I can use the limitation technique. As s goes to 0, so 1 over 2. use the tables and find y of t is 1 over 2 is a coefficient, so I bring it out. Then I have 1 over s, which is the u of t, minus 1 over 2. Then you have, I think, e to the power of minus 2t. I should check the table for this one, but I'm not 100% sure. Just yes? Yeah.
Can you explain the limits?
Limit technique?
Yeah, what you just did.
Okay, here I want to find A1 and A2, and these two are the two unknowns I have, okay? Because it's case number 1, the approach we learned is that we can use this limitation technique. This limitation technique says that you should take the limit of your original y of s or f of s, whatever it has the name, then multiply with the roots of your unknown. Here I want to find A1. So I multiply with the denominator of it, which is s, and find the limit as s goes to the roots, 0. But first, I need to do the cancellation if it's any there. That's why this s and s goes out. And now I put s equals to 0 there, which is 1 over 2. So A1 is half, 1 over 2. For A2, I do the same. The limitation of your big y of s times the denominator of your unknown, which in this case is A2, and times this, as s goes to the minus 2. Cancellation, and then you put s minus 2 here. So I have minus 1 over 2 as A2. And here, these are some numbers. So if I want to rewrite it, I can do that as y of s is half of 1 over s minus half of 1 over s plus 2. And from here, I use the tables because half is a number, I can keep it. The inverse LaPlace of 1 over s is u of t. And again, minus 1 over 2, I can keep it. And the inverse of this one, if I remember the table correctly, is e to the power of minus 2t times u of t. And that's why. Yes?
Yes. At the green part you've written at the top, the denominator, I noticed that you've changed it, and I know that you did it because you need to simplify the partial fraction expansion. But how exactly is it that you overwrite the previous one to the one you have now?
So you mean, how about if I don't do the cancellation?
Not necessarily. It's more how you reach the how you got from the previous denominator to the new one.
Okay, you know, first of all, if you put this equals to 0, you get 2 roots for it. So if you just put the parentheses, I will put it here. So if you put s2 plus 3s plus 2 equals to 0, automatically you got 2 roots at minus 1 and minus 2.
Yes.
Another thing which you can do is that when you have the roots, you can always write it as s, some terms which create the roots for you. So you can write it as s plus 1 times s plus 2 equals to 0. So if you do the multiplication, you get the same expression as above, okay? This is another one, and something which I learned in my high school, and usually we do, is that if you look at these two numbers, 3 and 2, if you can find 2 numbers which the multiplication is here and the summation is a coefficient of s, then always you can write something like these 2 parentheses for it. This is a general formula, and you can use it for any other second order polynomial. So of course you have some number as a coefficient of s. Here the coefficient should be always 1. But we look at here and here. If you can find any 2 numbers which multiplication of them gives you this, and the summation of those 2 numbers gives you this one, then you can always write it in this way. This is what my math teacher told me maybe 100 years ago, and still I use it. And it's true, valid, always.
Just one last thing then. Down in the parenthesis at the bottom, No, down to the right.
Okay, here.
That part just went through this. So it says s plus 1 because one of the roots is s minus 1.
It's minus 1.
Yes.
So what does it mean?
It means
so
it becomes
if you put
0.
this equals to 0, it gives you the minus 1.
Yes, and then
And
it's the
if you
same
put this
principle.
one equals to 0, gives the other one.
Okay, now I'm with.
Yeah. Before going to here, someone was here with a question. Am I right? Or you forgot it? Okay. Just ask. Yes?
I didn't understand your technique. Can you explain it in some other way? Because
Okay. I try again. So you have the second order polynomial equals to 0. And the technique which I'm explaining, the coefficient of s to the power of 2 or the power of 2 terms should be always 1. And again, maybe you have some numbers here and there. So if you want to write it as a multiplication of 2 parentheses, always look at these two numbers. One of them is 2 and another one is 3. So if you can find two numbers, which the multiplication of them gives you this one, and the summation gives you the other number, then you can write it as s plus those two numbers. One, you can see if I multiply 2 by 1, it is 2, so it is this number. And if you add 2 plus 1, which is 3, and it is this number. So these two are exactly the same mathematically. Yes?
You remove or you would have another fraction with s plus 1. How did you remove that?
You mean here?
Yeah, exactly.
Okay, this is s plus 1 in the bottom, and here you have s plus 1 at the top as well. It's like what you have this x over x, which we can say, or maybe x over x2. This is one maybe good example. Are you agree that the x at the top can be cancelled out with one of the x down here? So it is 1 over x now. And here I have s plus 1 over s plus 1. So these two cancel out each other. And that's why I did the cancellation. Any other question?
Der er 2 x.
Yes, please. Of course, that's my plan. We can have 15 minutes break, and we're back to the room at 9:15.
Can I make you